Okay, so now let's talk about the auxiliary space complexity. So auxiliary space, or also known as stack depth in some references, is the additional program stack memory that we need for our algorithm or function to function. So it's most of the time denoted as M of n. So similarly to time complexity, auxiliary space complexity describes the growth rate of the needed auxiliary space that our program or algorithm needs. So similarly, we use the various asymptotic notations such as the omega, the theta, and the big O notations for the analysis of auxiliary space complexity as well. So far, you may only have encountered algorithms that require a constant amount of space to either store temporary variables or some counters. So more or less, the complexities of the functions we've been dealing with have been constant, both at best and worst cases. So, however, for recursive functions, when we call, for example, the factorial of 5, it calls the factorial of 4, and then it calls the factorial of 3, and 2, and 1. And only once we finish the execution of factorial of 1 can we remove these factorial functions from our program stack. So each function call would need a constant amount of memory. And then when they are stacked on top of each other, it increases as we increase the number of function calls. So for example, if we get the factorial of n, we can expect that factorial will be called at least n times. And if we get the factorial of 2n, we expect factorial to be called 2n times. So we can say that the auxiliary space complexity is linear with respect to our input n. So the big O of our auxiliary space is just simply n. Now, it looks kind of easy just counting the number of function calls. So for our Fibonacci function, would that also be the case? So are we expecting to the n memory? Uh, that's not quite correct. Since let's see here, if we get the Fibonacci of 5, the Fibonacci of 1 actually terminates, and then we can already return already. So you might notice here that there will be a certain amount of memory that we will ever only need, and we don't actually need more than that. So that maximum amount of space that we need is accurately uh, measured by the depth of our function, of our recursive tree, actually, which is why we also call the auxiliary space as the stack depth. So the depth is the deepest level our recursion tree reaches. So that is the maximum amount of function calls existing at any during the course of the execution of the function. So more we don't expect the recursive function to use more memory space than that. So assuming each function call has the same amount of auxiliary space that it needs, and in this case for the Fibonacci function it is constant, we we can just look at the stack depth of the function or the deepest level of the function and multiply that with the space of one function call alone, And we already get the auxiliary space complexity of our recursive function. So that's it for the auxiliary space complexity.